Okay. Welcome, everyone. Welcome. Welcome to the 8th Beam meetup here at Google. I'm happy to welcome you guys again, some of you. Some of you are new faces, which is exciting. So tonight, I'll start with a quick overview of what has been going on in the Beam community. And then we'll have Isambar join us on the stage to talk about how they moved from Lambda to using Beam. And then we'll finish off the talks with David, who's going to talk about building an interactive streaming SQL engine in Beam. And then we'll finish up with awesome food. Yay. Who's excited about the food? Who's excited about the talks? Okay, cool. Nice. So what has been going on the last few months? We have actually had this thing happening in North America. It doesn't seem like, oh, there we go. So we had a Beam Summit in North America, which was super cool. And at the moment, we're in 6 locations in Europe now. So tomorrow, there's actually a Beam Meetup in Paris, if any one of you is joining. And later this year, we're going to Belgium, Warsaw, and Zurich as well. So super exciting. In North America, we also are taking off. So New York has had their first Beam Meetup this month, and LA and Boston are starting off later as well. If you want to stay in the loop about the Beam Summits happening next year, I advise you to refresh the beamsummit.org page now and again. On the Apache Beam project front, we also had a new release. I think it was last week. So we're gonna make these slides available, I think, after the meetup. So if you want to check that out, what new exciting new features are there, Apache Beam 2.16 is out now. If you want to make some noise on Twitter, do tweet pictures, any comments, anything you think is interesting. You can use the hashtag Apache Beam London, and you can also go follow these two handles at Apache Beam and at Beam Summit to know about the community part and about the technical parts of the project. I further encourage you very much to sign up to the mailing lists or introduce yourself on the mailing list if you haven't done that. And there's also the Apache Software Foundation Slack, where you can join and talk about Beam if you want to do that. Moreover, we have a YouTube channel, so in case you didn't make it to any of the Beam Summits in Berlin or Las Vegas was a bit too far for you guys, do check that out. We're going to post the Las Vegas one in a few weeks, I guess, and the Europe ones are already on there, so there's good content, so do check that out. So for tonight, we are at a great place. We are going to have great food, and this is all thanks to the guys at Google Cloud, and David has also kindly helped organize this evening. And I also want to thank the people from Datatonic who helped make this meetup and are still helping to run it. And then this was all for my part. So I want to introduce Isambar to the stage. He's a CTO at Huq, and he's going to talk you through what they did. And after that, it will be David. Cool. Thanks. I'm going to hand it over to you.
Okay, great. Thanks, Matthias. Okay, I've just got to work out how to use this thing. Like this. Okay, great. So my name is Isambar Poulsen. I'm one of the co-founders at Huq Industries. A little bit about me. I've had a pretty varied background, done a bunch of different stuff, but for about the last 15 years, I've been working in tech, principally mobile. So Huq Industries. Huq Industries was founded in 2014. We're essentially a geolocation company. We use mobile data to build analytics, models, predictions for a variety of verticals. So we sell into finance, both quantitative and fundamental funds, property, we do consultancy, aid with planning, outdoor media, essentially any application where you want to be able to look at the aggregated behaviors of people at scale and look at analytics about those. We've grown pretty rapidly in reach and data volume in the last few years, but essentially the team remains very, very compact, and that has had quite a lot of impacts in terms of like the choice of technologies that we used. what I'm going to talk about this evening is our most recent tech migration, which has been from Aws Lambda to Apache Beam. So just cover briefly how the data flows onto a platform. So we consume mobile data from a variety of sources, and we bring that onto the platform in form mostly of Nginx logs. We perform a variety of cleaning, processing, enrichment, deduplication tasks on that, and then we make it available to clients in a variety of different forms. So you can buy either the row-level data, or you can get access to dashboards, access to the data via BigQuery, essentially pretty tailored depending on what clients want and what their level principally of in-house data science skill is. So, this talk picks up like quite some way through our company's development. By this time, we've already iterated through several product life cycles. We've gone live with various, as you do in startup, various different possible products. But at this point, we'd kind of, I wouldn't say we pivoted, but you could say that our requirements had shifted. And so at the point I'm talking about, like, these are essentially our requirements. So we no longer had the necessity to serve data in real time to clients. 48 hours behind real time is totally acceptable for even our most demanding clients. So that gives us plenty of time to bring data onto the platform, do the processing, aggregation, make it available, check everything's okay, and then deliver it. On the other hand, there are things which are more stringent. So one of the principal things is that we need to be able to not only handle the volumes that we are processing in the present time, but also anticipate growth. So we've been in fairly aggressive growth, which is typically, several 100% year on year in terms of volume, and we want to be able to continue to serve that without disappointing our clients. And thirdly, we need to be able to reprocess our historical data. So we are constantly making changes to the code base, but many of our more quantitative clients need to be able to have the full history of our data processed in one single way. So what this means is that in order to avoid getting frozen at a certain point in the development cycle, as we continue to make developments, we can then reprocess all of our historical data in using one single code base, and then make that new version additionally available. So, yes. So, just briefly talking about Aws Lambda, I'm sure most of you are aware of what it is. It's a microcompute service made available by Amazon. Essentially, you can run pretty much whatever code you want on it, but that must be invoked and last a maximum of 15 minutes. And in those 15 minutes, you can do whatever you like. So you can do external database lookups, you can map data, write, read, essentially whatever you want. And what's really nice about it from our perspective is that it's serverless, scales really smoothly. So in this previous architecture, this is what we would be looking at. Data comes onto the platform. We consume that on Nginx running inside Docker. So we can spin up as many of these guys as we want and handle as volume changes. And then we just dump those logs straight into an S3 bucket. What's cool about Lambda, if you haven't used it, is that you can attach triggers to a bucket such that when a new file is written there, Lambda is invoked, it will pick that file up, process it, and then we can do external database lookups, etc. And then finally write the processed data again to S3, and more recently also to Google BigQuery. So this is really awesome for us because essentially, as the volume grows, you just put more data in the bucket. And every time you put data in the bucket, Lambda is invoked and runs and processes that data. If you need to reprocess data from a point in history, for example, if something broke, all you have to do is just dump those log files back into the bucket, and essentially it runs kind of without pretty much any provisioning at all. You make updates to the code and you just push those to AWS, and that's it. You don't have to provision any infrastructure. Cool. So just to reflect on some of the benefits of AWS, really smoothly auto-scales. This is the principal reason for choosing it in the first place. Very, very simple to deploy and manage. And also the cost scales very, very smoothly. So the majority of the cost of Lambda is on the processing time you use. So if you invoke Lambda, most of what you will just pay for the amount of compute that you use. So if the Lambda just stays up for 3 minutes, you'll pay for 3 minutes. If it stays up for 12 minutes, you pay for 12 minutes. Almost all of the cost is associated with processing time, and very little is associated with invocation count. So you don't really have to worry about that. So it was very, very good, but nothing is perfect. And so some of the issues that we were facing were principally around stability. And I think this is maybe in our use case, and you probably could build better implementations, and you certainly could do it in a way which would mitigate some of this. But what we would find is we would, say a Lambda fails, we would set it to retry in order that we didn't get a black hole in for that piece of data. But that can often exacerbate the original problem that caused it to fail in the first place. So if that's, for example, an issue to do with database connections, then the problem will only get worse, or database timeout, load, etc. So then you would get Lambdas retrying, you'll get more connections, the problem would just basically get worse and worse. So essentially for us, it was sitting in this, what I think of as like a locally stable state, where if it gets pushed out of that locally stable state, then it becomes essentially doesn't naturally auto-recover. This led to us generally over-provisioning the database in order that you could cope with such spikes and you wouldn't get those kind of issues, but that's not really very cost-effective in order to do that. And then finally, there's a hard limit, an upper limit on how many of these you can invoke, which I think is about 1,000 concurrently. Some limits it is possible to raise. I don't think this is very easy to get raised. So that is fine in terms of a day-to-day processing volume, but when you're starting, we want to like reprocess, we're now in the kind of many tens of billions of records layer. You want to reprocess all of that history. It's no longer very time efficient to do that. We were able to do that in days. So these were, some of our motivations when we were looking around for alternative technologies. Ideally, we'd like to be able to do this thing. We did run green-blue architecture on Lambda, but again, then for each of those like pipelines, you need to have your own database. It quickly becomes quite expensive. So we would like multiple parallel pipelines. We want it to be really resilient. Essentially, none of us want to be woken up on a Sunday morning to fix stuff, and that happens a lot, or has happened a lot. It would be really nice to choose technology, which, of course, nothing is ever going to work all the time, but which is highly resilient. And then finally, as I've already mentioned, this kind of pace of reprocessing. So ideally, we would like to be able to push out new versions and then rerun our full history extremely rapidly. So, we started to read about Beam about a year ago when it was still only supporting Python 2. I'm sure most of you, if not all of you, are fully aware of what it is. But it seemed that it could potentially solve quite a lot of the issues that we were facing. So why did it take us so long to start using it? I mean, why hadn't we used distributed processing architecture before? And I think that's principally around kind of like the learning curve or the barrier essentially of migration. We had previously iterated and done code migrations, but they were kind of iterative. You could think of them as being incremental. We'd gone from like single tenancy to serverless, but essentially the code had stayed similar in form. Beam is obviously a paradigmatic shift in some ways. You need to not only you need to think differently about how the processing takes place, not only to have your code written differently. So there was a lot for us to learn, and there was a lot for us to rewrite. We have quite a lot of code, although the schematic I've shown you is simple. We have lots of processing, lots of different things happen. We co-locate individual events. We do lots of lookups against external data sources, etc. So we wanted to be in a place where we were very comparatively stable in terms of fixes to the current infrastructure, change requests, etc., in order that we could devote a reasonable, a healthy amount of time to the project without like knowing that we're going to be kind of distracted or start having really nasty stuff happening, like making changes to two separate pipelines simultaneously. So that was kind of why it took us some. So you probably know, anyway, I'm just going to briefly run through how Beam is like essentially as a set of transforms which get applied to a data a stream of data. So in more conventional programming models, you essentially would pass some data to a method and that would return you some other data. Beam programming model or distributed data model programming models in general are different in mindset in terms of the fact you have to visualize your data as a stream which is continuously being passed through a set of transforms. You can't capture that at any particular kind of state at any different point. These transforms can like reorganize your data records in different ways, or they can process, essentially transform individual records as they're passed in. So anyway, you probably know all that. We run, with Beam, you obviously can run on lots of different infrastructure, runtimes, Spark, Flink. We choose Google Dataflow. Sorry, these slides are a little bit chopped down, but anyway. And many of you may also be doing that. But we chose it. We're a tiny little team. There's 3 of us, and we want generally solutions that are fully managed or at least mostly managed. We don't have time, essentially. We just don't have the resource to manage our own infrastructure. So it's fully managed. It's also highly scalable. So you can have, I think, any individual job. I'm probably going to get some of these numbers wrong, but anyway, any individual job I think can run up to 1,000 different instances, and each, even in the general compute engine instance, can be up to 96 vCPUs, and you can run up to 125 concurrent jobs. So that's like a lot of power, and hopefully would manage even our potential future requirements. Just going to briefly touch on like some of the Beam processing methods. Essentially, within Beam, you have like a big catalog of different transforms that you can apply to your data. Those can be used to reorganize data or transform individual elements. I'm only going to cover this because we're going to talk about it in a little bit. The generic one of those that you can most commonly extend is the Pardue. So basically, this is a class which can be used to handle any individual processing element. And really within the model, this is where you have to do all of your processing. So for us, this was quite a big thing to get your head around. There is no overall state of the application to which you can refer. You just have this individual block, and where, whatever you want to process, you have to do inside here, and whatever you want to refer to, you have to somehow get into here in order that you can refer to it. So there's no like having static, consistent variables or mapping tables hanging about that you can refer to, basically. Just going to talk about this main interesting part of this was about some of the hurdles that we've experienced in our migration and how we solved those. So we're a location company. That means we use a lot of geospatial information. And so most commonly, we need to associate records with each other, either with mapping or say associating events that take place to places where those events take place. So we have to use a lot of GIS functionality. Classically, we are using Postgres RDS, so we could use just PostGIS, and then it's really easy. You just like have a target and you want to associate it with a bit of data. You can just look up on the database, find me the nearest relevant piece of information to which I need to apply my whatever it is, association. Of course, in Beam, we have no transactional database, and we certainly have no GIS. So what we would do in that instance then is build geohashes of the location information, and then you can just group those by key, essentially, to provide you with a short list of potential lookups that you need to do. And this worked really well for us. But of course, it doesn't always work. In many instances, you end up with this scenario. So you have like the piece of data you want to associate with, but your geohash, the associated piece of data are living in a different geohash to the one you are looking at. So in that instance, then we would join it to its neighboring geohash as well. In fact, you of course need to then do that for all 9. But so what we would build is a system where like the source data essentially is broken out into the 9 potential geohashes in which it can live. And then we associate that, we group by key with all of the potential, with the target data. And that works really well, basically. This was pretty smooth. And I think when we came up with this, and we were feeling pretty chuffed with ourselves, and then we came across these, which in case you probably almost always will have come across these. So this, like, you read about how when you want to group by keys, what kind of keys you should choose. And we thought we've chosen a really nice key. It's really well distributed. We've chosen like squares on the Earth, which are pretty similar in size. That should work really well. And it worked really well on some really small amounts of data. But once we started running it with whole days of data, which are kind of in the hundreds of millions of records level, it started performing terribly. Because, of course, the reality is that our data is human in nature. It's not about natural landscape, it's about people. And people congregate in different places. And some of those places have significantly higher densities than others. So, yeah, London, of course, you're grouping by, like, around here, enormous density of people. There's going to be a massive amount of data associated with it. The middle of the Sahara Desert, not so much. So in case you don't know why they're a problem, ideally you want to pick keys which are going to be distributed across your nodes equally, so that all of your workers are doing equivalent amounts of work. But if you pick keys which for certain ones of those are going to be hotter or have much more data associated with them, that's going to result in terrible performance, because essentially all of the data is going to get piled onto one individual worker. This has a number of impacts, performance being the first. Essentially all of the workers then have to wait for this guy to, because a key can only be on one worker. So have to wait for this guy to finish. It's also really expensive if you're running in something like Dataflow, because all of your workers stay up waiting for this guy to finish. So we had costs through the roof and performance through the floor. It was not good. So how can you solve this? Essentially, there's a couple of solutions. Ideally, pick some better key. Now, this would be great. Another key where your records are more evenly distributed. This didn't work for us because we can't really get around the fact that it has to be location that we do these things on. And so maybe there is some kind of magical way we could do it, but we didn't come up with it. So we chose another solution, which is basically split the data into smaller pieces. Originally, we'd been kind of scared of this because we thought, all right, we're going to end up with like just this crazy profusion of keys, and that's going to be terrible. So originally we'd chosen 1 kilometer squares to build our geohashes. But if you think about, say, the 1 kilometer square around here, or the city of London, it's going to have a massive amount of data associated with central Manhattan or something, a massive amount of data associated with it. By breaking those out into a larger number of smaller keys, so then we moved to just building the geohashes on 100 meter squares, you end up with, although you're going to have some of your keys significantly hotter than others, you have 10 times as many. So then they are like shared out across your workers much more evenly. And we did this, and basically the performance became radically better. So that was really good, worked out. So going to talk a little bit now about another thing. So side inputs, in case you don't know what they are. Probably do. Often you want to have, I mentioned that it's not enough, you're doing all your processing inside the Pardue. You want to be able to pass additional information often. In our case, we very often need to be able to do lookups upon that data, associate those elements with other things. For example, we do lots of enrichment based upon we change device models into their human readable form. So we have like lookup tables which work on those. So you can pass, along with the record in question, you can pass an additional piece of data which is static, essentially gets passed to every single processing element equally along with it. And that's great. But sometimes those tables can become pretty big. So we're often dealing with mapping tables which maybe are hundreds of K or even megabytes in size. So that means, what that means is every time a record is being passed to a worker, it's also passing a massive amount of data. So your record may be like, I don't know, bytes in size, and then you're passing hundreds of K along with it. And essentially, what was happening was like this was actually a bit more difficult to debug. It wasn't until we started looking at the network stats on Dataflow that we started to work out why it was that the performance had become so bad. Was that essentially we just like maxed out the amount of network processing. So we basically needed to find, well, we were kind of wondering if it was even going to be possible to find a solution for this on Google Dataflow. Of course, ideally, we would just have the data existing on the nodes themselves. But in Dataflow, you can't customize your workers, and you can't provide custom images for the containers that get brought. So our first thought was like, okay, we'll just build some custom containers. We'll bundle the data that we need into those containers. When Dataflow brings up the worker, like we'll just like load the data straight from the container. Unfortunately, that's not possible. It seems maybe it is possible, and we just didn't find out how to do it. But somehow we wanted to, rather than passing it every time, get the data onto the workers themselves. So what we chose to do was to, when the package is initialized on the worker, setup.py is run, and in setup.py you can run some shell scripts. So what we would do is essentially reuse those shell scripts to copy data from Google, from like GCS or from BigQuery onto the target machine. And then when your Pardue is initialized, this little start bundle method is called once for every bundle of records. Then you can just load that data from the target machine into memory, and then you just can pass a really lightweight key. So rather than passing the full mapping table, we'd just pass, potentially just a number or whatever it was that we would do in order to do that lookup. And then essentially this way, we could do exactly what we were looking for without incurring that massive, nasty network overhead. Yeah, that was that. And finally, we were often, so we would be using external data sources, and sometimes those were like mapping tables. They wouldn't need to be changed essentially during the processing pipeline. But some of our data does need to be changed. So often we are looking up records against transactional databases, and those transactional databases also need to change. So it's not only the data we're streaming that we're ingesting that needs to be processed, but we also need to write persistent changes to other data sets. And essentially the solution we chose here was merely to then load those. Before that was no problem, of course, but merely to load those transactional databases into separate P collections. So then you're running like multiple P collections together. We have our stream data and then our transactional data all running parallel in different P collections, and essentially using that P collection kind of like a transactional database, writing changes in there, and then at the end of the pipeline, writing those back to either Google Storage or BigQuery. And this works really well for us. I think it worked. We run our pipeline as batch. If you were running it streaming, I don't know if this solution would be so appropriate, but I'm sure you could find a way. So yeah, just going to briefly go over now what our current architecture looks like. So we may now make changes to the code base and push those to GitHub when we want to create a new version of the pipeline. We just increment our version number, push that to Circle CI, tests pass, and Circle CI then essentially pushes a new template with all of the new code to Cloud Composer, which then generates the Dataflow pipeline, the Beam pipeline, and results finally get pushed to BigQuery. The really nice thing now is that we can have completely independent pipelines. So we want to create a new version of the code, of the data, which clients can then optionally, smoothly upgrade to. We just basically increment the version number, we get a new template, we get a new pipeline. We can run as many of these in parallel as we like. It's awesome. So there's been lots of benefits, I would say. I don't have another slide for this, but to our migration, which is not yet fully complete. But one of the main ones has been that it's forced us to consolidate our code base, essentially. So although in some ways we now have a system that's more sophisticated, we've had to overcome certain challenges. We now have all the code written in one place, and it's really obvious, essentially, what is going on. You can just like read through it as a single flow, and that's been like a kind of unexpected positive. But yeah, essentially, been so good so far. So yeah, we're not fully out of the woods. I think we're going to have some more issues to navigate before we can like transfer everything to this infrastructure. But yeah, it's good. So anyway, that's it. Unless you've got any questions. Go for it.
How do you do updates, rolling updates? If you can maybe like that.
Yeah, we're recording, so we can actually.
Sure. How you do updates to your data flow if you have some graph changes?
If we have some graph changes.
Some updates to the processing pipeline, basically.
Okay, so essentially, we have so when we basically run from Cloud Composer, from Airflow, and those we could then have templates that are running for each version. So each version then has its entirely own code base that sits within Cloud Composer, and when it gets invoked, that is run with the code base that is running for that particular individual version. Essentially, so what is being invoked are multiple distinct versions of the code base, essentially sitting at different release points.
And then you kill the previous one.
No, we run them because essentially we have clients who. So say you were at like version 1.23 of the data, people may well have done something like trained a model against that data. They want it to continue to be processed in that way, so we leave them all up, essentially, until we. Are at a point where there's stuff that's obsolete and no longer needs to be maintained, essentially.
Hi, thank you for the talk. It's very, very good. I have a question here. Are you ingesting the data directly with Dataflow, or are you using cloud storage before the ingestion?
Say again?
Are you ingesting directly with Dataflow?
Okay, so this isn't a very good diagram for that. Dataflow is ingesting the from cloud storage. Yes.
Okay.
Yeah. So this is kind of a schematic that shows the more like the flow. Kind of informationally. Yes, the data is actually being pulled from GCSS logs, Nginx logs.
Yeah, makes sense. Yeah, thank you.
For questions, there's also fancy stickers, so I encourage you.
Can you describe a little bit more about the reason you needed the keys?
Mm-hmm. Like the use of geohash keys?
To group data?
Yeah.
Your keys, some maybe implementation details.
So basically, some of your Beam transforms. There's like often you want to associate lots of records together in some way. So we often want to associate all of the records that maybe have been associated with a single device. So then there is a call transform, which is just called group by key. And so essentially the key in that instance might be a unique device identifier, and then we can run group by key. And then essentially we have all of the records in one place. We can associate those with a tuple, for example, pass them to a Pardot and process them all contextually in one go. In the instance of where you need to match two different sets of data, there's another transform which is called co-group by key. So essentially you create keys for both different data sets. which are matching, which match each other, and then you run code group by key, and then you end up with all of the records that are associated with those respective keys from the different data sets together in one tuple, essentially.
Did you try stateful processing?
Stateful processing in Beam? No, I don't think so.
It's like storing intermediate state for your actual keys.
Okay, so yes, so we have lots of our lookups basically are stored with the key that they're all. So yes, we often, like, we are loading the data and saving the data together with keys that are not generated on the fly. They are the keys that we are going to use. Essentially, you wouldn't be able to port it to another system. We're associating, saving those together with the keys that are going to be used to associate the data, basically. So yeah, we don't create them on the fly. They are already saved and loaded within the, yeah. So yes, kind of.
More questions? Maybe a question for the floor as much as yourself. You mentioned about you couldn't load the database data onto the workers on startup. I think in 2.16 it says something about custom containers. I'm not sure where the limitation is in being able to use custom containers. But maybe
yeah, I don't know the answer to that. In terms of custom containers, the limitation insofar, but I would be fascinated to hear from the Google guys, the limitation that we had was from the Dataflow side rather than from the Beam side. So yes, it was that we couldn't use Dataflow you couldn't use container registry. We couldn't just push some image to the Google container registry and then load that, which would be awesome if they would do that.
Yeah, I can cover. Hello. Yeah, so at the moment it's not supported. So that's part of the portability roadmap. So whenever we have that available as well in the Dataflow runner, then that's one of the key things is to be able to run containers.
Yeah, that's good.
So your own images and all the stuff. Yeah, that's really in the roadmap. But yeah, at the Beam framework, you have that available, but it's not compatible with the Dataflow runner at the moment. Yeah, cheers.
Great.
Any more questions? Oh.
Just a simple one. What language is your code base?
Oh, it's in Python, yes.
2.7?
No, because since Beam 2.1.4, I think it was moved to Python, started supporting Python 3. So this was a massive pain for us because, like, all our code was Python 3. And then we were like, oh, great, we're going to use this Beam thing. This is rad. Like, guys, like, this is only supporting Python 2. What's going on? And, like, it was, yeah, it wasn't actually as bad as all that. But we did have to back migrate our code base. That was one of the things. And now we've forward migrated it again since.
So that's supported under Dataflow, not just obviously the latest
It was Beam version 2.1.4, I think, that started supporting Python 3.
Right. Okay,
Yeah.
thanks.
Yeah, no, absolutely. It was like, yeah, what's going on? Python 2 is going to be like EOL at the end of this year, I think. So, cool. Thanks.
Cool. So we'll give the floor to David.
Oh, sorry.
Let me open up. I'm going to do a bit of a demo as well, so let's warm this up as well. I will switch later, so that's really took a bit open. Okay. Building and drafting streaming SQL engine. So yeah, first of all, my name is David Sabater. I'm a data analytics specialist at Google, and I'm going to talk today about the streaming SQL in Beam. Let's just look at the agenda first. We're going to talk about the who, the what, where. You know that in Beam we always try to get these subjects, so we're going to try to address in that way. I'm going to run a demo with the SQL, the Beam SQL CLI, the client. Then we're going to talk a bit of a deep dive if we have time. And then I'm going to also do a demo with our Dataflow Sequel Ui. So you're going to show I'm going to show the very similar use case with the client, and then I'm going to show as well that how you can run that with a Dataflow UI. And a bit of what's new regarding SQL. But we talk about Python, and in the last release in 2016, there have been a hell of a lot of new Python announcements in terms of streaming. It's GA, so fully supported, and also you can autoscale is also supported. So it's very nice set of the guys. They made a really great work. Okay, let's start with Huq. Who from you are using SQL on a daily basis? Can you raise your hands? Okay, I'm trying to find someone that doesn't. So it's everybody, right? So every one of us, at some point in time, we need to use SQL, right? So it's the lingua franca really for really any of the work that we are doing with data. So basically, SQL is a structured query language. So it's really how you will query your relational model is just using SQL, right? Basically, it's translated into a set of a relational algebra. So basically, when you have a select, you do that as a projection. When you do filtering, you do aggregation, a group by. All these things they have very well-defined steps, right? In the SQL, in whatever SQL engine you have. So that comes natural that we should just implement the same thing in Beam, right? So that's really the idea here is you typically have this type of pipelines, right? You are joining data from different sources, and then you aggregate. Basically, you are doing SQL, right, to some extent with your P collections. So that's really what we want to do here is that build a framework that is actually helping you, facilitating you to actually do that. So basically, the characteristics of Beam SQL is to be able to support any type of size of data, right? So similarly, when you're doing P collections, sometimes you are co-grouping, doing a join, or sometimes you're doing a side input, depending on the size of each of the data sets that you are joining. The interesting thing is that Beam SQL is not built on any storage. So Beam SQL is working on the data that you have on the flight as you define in your workflow. So that's all defined there. So you don't really need a backend for that. But obviously, you need a data source, right? So you need the data to come from somewhere. So we also have a set of data sources. In the particular demo I'm going to do, I'm going to use PubSub for the events, and I'm going to use BigQuery to enrich the data and also to insert the data, okay, as the sink. But you have other, you have buckets, S3 as well, and you have other open source frameworks to use. It's meant to actually leverage costs and different metrics. As an optimizer in SQL, you typically want to rely on these things, so that's also being part of, it's going to be part of a Beam SQL. Basically, on the cost part, right now, we are defaulting all the costs by one, I think. So we are trying, this is actually one of the new features that we're going to be able to actually split that much better when we do the joins. So we're evolving on that one. And obviously, the most important thing, I believe, is that supports streaming. And I think that's super powerful. OK, so yeah, time is always important when we are talking about streaming, right? So the key thing here is that when you represent that as a group by within your SQL query, you need to actually think about your windows. So windows is when you have stateful aggregations, you need to think about how much of these events that are arriving, you will need to define a finite window on where you are actually aggregating these values and then emitting them, right? So that's the thing that you can actually apply with a group by. You can define different windows strategies. So similar to what actually, well, equivalent to what we're doing with the Beam with P collections normally. So tumble window is actually fixed window. That's kind of the Flink SQL jargon, and it's more typical in the SQL environment that we talk about tumble windows. It's like a tumbling in the window. Then we have hop, which is sliding window, and then session, which is the same one as P collection is a session window. Windows Over is not still supported, but the other ones are, okay? So that's how it looks from the SQL client perspective, which is the first demo I'm going to do. Basically, I don't know if you're familiar with Spark SQL, the Spark Shell SQL. So it's very similar. You interact with typical SQL, the semicolon to actually finish your statement, and then you keep going. You're setting things like, for example, which runner you're using. So in this case, we're using direct. We create some temporary tables or external tables, and then we switch to run the next thing actually from Dataflow runner. So it gives you that flexibility to interact with your data. So this is more about, it's not really like a notebook, but It's a way to interact with your data while you are prototyping your pipeline, which is very helpful, right? So this is kind of a way to debug your schema definition, your data, to make sure that when you implement that into your pipeline, that works as expected, right? So now, can we switch to demo, please? I'm gonna run a demo with the client first, okay? So what I have here is, this is the shell script, okay? You don't see too much, but sorry about that. I tried to increase the font, but it's just increasing the box only. So we are actually using Beam 2.16. It's all in the official documentation about how you need to build with Gradle the shell, so then you can actually run that. And the next thing I'm gonna do is, I'm gonna show you the set of commands I'm gonna run. And I think you will see them better from here, yeah. So basically, I'm gonna copy paste all these statements, but for you to better view what I'm gonna do in the shell client. Basically, the first thing I'm doing is setting the GCP project. At the beginning, it's not important, but for some of the actions I'm gonna do when accessing the Dataflow runner, I need these details, so I put it there. Temporary location, bucket when I'm gonna be pushing data to and from GCP, and I'm gonna start with direct runner. So I'm gonna start locally from my laptop. I'm gonna start interacting with the data, okay? So the first thing I'm doing is, this is DDL, like any other SQL client. I'm gonna create a table called transactions. This is actually a PubSub. It's pointing to a PubSub topic. So I'm actually creating a representation of my events, okay? These two event and attributes, they come by default from the part of the structure of PubSub messages, so we cannot change that. Our interesting part is the payload. That's what we have control. On the other tab, I actually have a Python script that is gonna be pushing events, random events into that PubSub, and it's actually this payload that I'm introducing here. Basically, timestamp and then a bunch of names and other details about city and state, and an amount, a number, okay? So that's the location of actually the topic, which is in GCP. And what I'm gonna do also is I'm gonna create another external table, which is actually a BigQuery table. You can see that the type is BigQuery, and the type here is PubSub. Location is the project dataset and table. And this is actually a nice new thing that comes from the 2.16, is that there is a new method in BigQuery, well, not new method, but there is a new API in BigQuery that you can actually export your data directly without having to go through GCS. So that feature is also available from the client, and where you actually skip pushing data into GCS first. And then I'm properly running queries. So I'm gonna try that now. So let me be lazy and copy paste all this stuff, because I don't want to. I have a very bad memory, so I will. So first I'm gonna kick off the little script I have. So basically this is inserting any random amount of time within 5 seconds. Is also inserting the kind of events that I described there, that they go directly into PubSub. So what I'm doing here is, I'm gonna copying all this. So whatever I show you from the notebook, the notepad, sorry, is what I pasted here. So nothing different. So that's the query. Now it's actually running things locally. So if I'm going, because probably you won't see too much, but if I'm going back to this and I highlight the query, it will be very interesting, because what I'm doing is, again, a SQL statement. I'm actually projecting what I want to select, the columns, the whole payload, plus the sales region from that reference table that I loaded from, or I created to a reference from before. And I want to do an inner join based on the state. So what I'm doing is enriching the events with information about the region based on the state, okay? So that's basically what I'm doing. I'm putting a limit 5 because that's a way to control, this is the trigger notion of the processing time. It's actually based on how many events you received. So that means that after 5 events, I will actually show the results. So hopefully, if I'm going back, yeah. I can see that I got 5 results. All I did is enrich the data. Okay, so we see that, what is the state? Yeah, the sales region. We added the different types of regions that actually they come from BigQuery. I did that locally. So yeah, that's one example. Now, what I want to do next is, okay, that works, and I want to do it at big scale. I want to do it in Dataflow Runner, and actually, when you submit these things into Dataflow Runner, you need to actually insert into a BigQuery, because you don't want to actually, again, throw that into the standard output, because actually will blow up, right? So the next thing then is, if I continue here, checking the time, I think we're okay. So now I'm switching gears. I'm saying, okay, I'm going to use Dataflow Runner, and I'm going to use Europe. So that's, I think, Belgium. Okay. So I'm now creating the target table. Okay. That's another create external table. And also I need to point to GCP temp location. That's when I'm actually inserting back into BigQuery. It first needs to go to a staging area into GCS. So that's what I'm doing here. Okay, good. Now I'm gonna do it's exactly the same select, but all I'm doing is on the top I'm just saying insert. So let's imagine that previous one was over a sample of my data, and then this one is for real. This is over terabytes or petabytes of data. So I'm gonna run this one. Obviously, we are still talking about same size in this case, but it's to give you an idea about how you will interact. So in this case, now we're triggering. Oh, okay, yeah, that makes sense. The table is not empty. So I need to go quickly to my table and because the default setting is to actually make sure it's not there. So I'm gonna the SQL table cells. I'm deleting, and I'm gonna create it again empty. Well, I don't need to be. It will create the whole thing. So I'm gonna try again. I still keeping, yeah. Okay, so that's triggering a Dataflow job actually on my project that I have set up on my SDK. Yeah, so you can see that at the end it just said, okay, I submitted the job. Obviously, that's a client shell that you can actually use for prototyping. So if you want to actually look at what is the job doing, you need to use gcloud command. Actually, more easy, we can go to the UI so you can see, guys, properly what is going on. So if I click here, let's see, I'm in the right project. Yeah, so now it's spinning up the DAC. Okay, so now it's spinning up the workers and doing all the stuff. What is interesting, and I will talk now about that in the next few slides, is about how we split that SQL statement into the different relational algebra steps that we need to do, right? I will go into detail, and then I will go back into this graph, and we'll see the results, and then I will do the same thing from Dataflow, so we can see all coming together. Can we switch back to the slides, please? Thank you. So the job will take about 2 minutes to complete, because it needs to spin up the worker to actually do the stuff. So yeah, let's go a bit in detail about Beam SQL. We have about, I think, 20 minutes, something like that. It should be, yeah. I will probably skip some of the things, but we can actually catch up later if you want to go a bit more detail. But essentially, it's Calcite. So I don't know if you're familiar with Calcite, but Calcite is actually a framework to actually parse and analyze and create your execution plan from a SQL statement. So it's kind of using SQL ANSI standards, and it's really trying to kind of have a common framework to actually do that parsing, okay? The other engines, like in Spark, I think it's called, what is called? I don't remember now the name, but it's a different one. It's not really Calcite, okay? So it's they have their own parser. So basically what we're doing is we get the SQL statement, and then we parse, and then we split it into the different parts, the projection, the filter, the aggregates, all these parts, and the joins, and we convert into relational algebra. That means that we you use a language and then you extrapolate that into an abstract, what is called an AST, an abstract syntax tree, which is a DAC, but with some abstract representation of the logic that you're doing, right? So it's not like something common to Calcite or to Beam. It's like a common way to represent that logic. We obviously convert that into an execution plan. In the case of Beam, what we're doing is P transforms. So ultimately, all gets translated into a P transform, which is the way we interact with the P collections. The P collection needs to be in a particular format, a row format, which actually, I don't know if you're familiar with the schema P collection that Ruben talked in two meetups ago. And it's all powered by schema, a schema P collection at the end that gets into a row, and that row is what you can actually represent and apply your logic. It has also a JDBC driver, and that's really what is allowing me to actually have the client shell command, is because you have that wrapper there. So it's really using that. There's a bunch of SQL operators you can use from Calcite, or we also implemented the ones that are required for Beam to translate the SQL ultimately into the Java code that does the filtering and the projection and all the stuff and the joins and the group bys, okay? Which is the last part, okay? So paths, I described one path, which is really the client command, but the one that you typically implement when you go to production is to actually have that SQL statement included as part of your pipeline, but within a SQL transform, and then you call that SQL statement there. Okay, so it's different because there is more interactive. Here is more about, okay, now I know my SQL statement is right, and I know the type of data I'm expecting, so all is working. So I can actually ship that into my pipeline and make that part of the whole pipeline, right? So the way it works, as I mentioned, is parsing the AST, the tree, validates things and converts into logical plan, checking all the things about cost, which, as I mentioned, is all defaulting now. And then at the end, it converts into a physical plan, which is really the Java code that gets executed in the pipeline and with whatever runner you are using. Okay, for example, I used direct runner and then Dataflow runner. That's path one. Path two is what I described. In this case, you are not really using any Java SDK. You go directly through the JDBC client, and then you inject the SQL, it gets parsed, and it actually does the same thing, exactly the same thing, and ends up being code, and that gets executed, okay? So that's really, you see there what is Calcite doing, right? So that's quite key. And all these boxes is Calcite doing all the stuff, which is really good. Yeah, so this is what really the parts that Calcite manages, and also the things that we had to do. The main thing is Calcite is abstracting all this relational algebra. So the main nodes that you get is always filter, project. This is a filter, and this is a select. So this is when or a map, when you select this particular columns or elements. That's what you do there. A join, an aggregate, values, and then table scan is to actually source the data. And table modifies to actually sync, right? So you can see that it kind of matches very nicely with what you will always do in your pipeline, right? So if we see the Calcite model, kind of a canonical or abstract model, we see the filter, the table scan, the join. So everything fits together, and this is a very nice DAC, right? So if we transform that into a Beam model, it matches nicely. So it's really pardoes for these parts. We do a co-group by key. And then we combine as well if we need for the sync to be compatible with the sync, and with the other sync if we have another P collection there. And that can be applied to bounded or unbounded, because again, this is a way, Beam is actually a framework to actually unify join, streaming and batch mode, right? So that's very nice because with the same concepts you apply to streaming or batch data. And that's the whole part of the pipeline. Now, we did a bit of optimization there because one of the things is to simplify how you transform all these things into P transforms. You can combine these things. This is kind of a fusion that we're doing, not really fusion because this is already part of the when you actually convert that into Java code. But we call that a calc. So every node is actually a calc. And for these two type of operations, we combined them because you can do that. And it's much easier then to do translation into a Beam node, which is, you can see here the different types of the calc, as I mentioned. This is the filter plus project. You have a join, an aggregate, values. This is enumerable. That's really when you're running a query, you create an iterable for your rows, and then you go through that, through the rows. So that's really what is the enumerable. It's an iterator for you to go through your rows. Yeah, and as I mentioned, the rel nodes are actually P transforms, right? So yeah, as I mentioned, the beam calc is a Purdue. So at the end, you do, as you described it quite nicely, you introduce Purdues. So we are actually leveraging here Purdues with your whatever transformation you're doing there, being a projection plus a filtering, basically. Yeah, with from 2.10, we started to use a different way to generate the code, very much a better way to optimize that code generation, and also we introduced the interpreter that I was just using. Yeah, and then we're using the call side built-in functions to use that, right? So that's basically what we're doing there. So this is an example to see. Basically, this select statement gets transformed into this Java code. So just to see an example of doing that. So basically, what is that noise? Like cooling down. So we are projecting these guys, and then obviously we are doing a filtering here. So we do all as part of the same P transform, right? So we do both things. Okay, so this is about how we ingest and how we actually write the data. So basically what we have here is we can actually connect with P collection, existing P collections with the type of elements being row. You can connect to that directly, and then you can actually ingest them and do whatever SQL statement you want. Or we have DDLs that actually, as I showed, you can actually create tables as external table and then connect to PubSub, to BigQuery, to a CSV file you have locally, or a file that you have in GCS. So you can do any of that with, or you can also, as I mentioned, with Kafka, and with text.io as a CSV. Okay. This is the enumerable that I just mentioned. This is really just to obtain an iterable that when you are querying your data, you can actually iterate through the rows. And also when you get inserts and things like that, when you get the metrics about how many inserts, how many rows you inserted. Okay. Now switch to demo. Can we switch to demo, please? Cool, cheers. So I'm back to what we were before. I will just refresh. So this guy is still running, and if I'm running a query again, hopefully, this is my project. Yes, I'm gonna refresh again. So yeah, I have a new nice table here, and if I'm doing a preview, you remember I deleted that table. Now it's back there, so there's no magic. So let's do a query table, which is faster. Okay, you see the data there? So that data comes from the PubSub, and that's the Dataflow job that I submitted from my client command shell. Okay, so a bit of jumps, but you can see that you can start the experimentation locally. Then when you're happy, you submit that, and then now we have a streaming job that is actually capturing anything that comes from PubSub. It actually combines with my reference data in BigQuery and inserts into a big table. Okay, now what I'm going to show you is, and I'm not going to rerun the whole thing because it takes time to spin up the workers, and what I'm going to show you is a different project. And here I'm going to use as I mentioned, the Dataflow Sequel Ui. This UI is in alpha, so it's a public alpha, so you can have access to the UI. And here what I'm going to show you is much easier because first, when you have a PubSub topic, you need to create a schema, right, on the messages that you are receiving. If you remember, I did that with a create external table. From the UI, what you can do is actually leverage one of the products called Data Catalog, and we can capture and register any metadata that you have on your project. So what if you follow at the end of the slides, I included links to the instructions to actually replicate that. So you need to actually register that schema, that JSON schema, into Data Catalog to say, okay, this is the format of my messages. And if I'm going here, once it's registered there, you can see that the transactions are there. So this is exactly what I described in the create external table, if you remember. So this is the payload actually with the elements that I'm pushing. Okay, so it's exactly the same thing. Now this is available from the UI. So what you can do is nicely, let me increase this font size. Much better now. So this is a much more interesting query, because here I'm actually aggregating and creating a group by a tumble window based on the event time that comes from the pops up message. So this is actually combining it's a stateful aggregation. So it's every 5 seconds it's actually doing that, and this is inserting directly into BigQuery, because as I mentioned, this is a distributed job like the one I submitted at the end there from the client. You can do that directly from the UI, so you don't need to actually mess up with the client. You can do all this stuff from the BigQuery UI, which is very nice because you start interacting with your existing static data. Then you can actually combine that with your streaming data that comes from pops up. So you can actually, this is always what we all wanted, right? So you get all the events, but you need to actually somehow put all these events into a table. Rather than putting the events into a table, you can actually join them as they come, thanks to Beam SQL, so you don't need a storage, as I mentioned, right? So you see that that whole join with a group by is already running. So I can show you quickly the graph, the DAG that is actually calculating that. So this is the new nice UI as well, by the way. So you get more emphasis on the system latency about what is your data doing, and then you can actually go back always to the lovely job graph, the DAG, where you see what is going on. Here we can actually open up, and you see the rel and the calc rel that I just mentioned before, right? So this is the source. So we actually table scanning, I think it was called, or we're actually ingesting the two tables, sorry, the event and the table. We're doing a join, and then this is a projection and a filtering we're doing, and then we are aggregating there. So we are doing all this stuff in the flight, and we don't need to worry about creating all these steps. By knowing how you will represent that set of steps with a SQL statement, Beam will create that DAG for you automatically, which is very nice. So this is running, so I can actually go to BigQuery and see the, okay, I need to go back to the job history and see the jobs running. So I can then open that here, and I can see the results in real time happening as they come through. So you see there, sorry. All these things are the results of that aggregation. It's not just that you are writing to a BigQuery table, but from the query that you just run combining the pops up with a BigQuery table, you can see the results as they come through. And by the way, this is using a BigQuery streaming API, so the results, they go straight away into BigQuery. So I think that's it. Yeah, that's all I want to show you. We'll have time for questions and other stuff. Can we switch back to slides, please? Cool. So that's for the two demos. That was plan B, just in case if things were not working okay, just to show you the UI. Okay. You always need a plan B, believe me. And then, yeah, the last one is what's new in SQL. So the first thing is, as I mentioned, in 2.16 we introduced that logic that basically is able to do project and filtering pushdown, because the storage API, when you define your query to extract data out from BigQuery, you remember the create table, blah, blah, that I did at the beginning, you can instruct which columns you want and which filtering. That data that comes directly, it will be already filtered, right? So you are not really, you minimize the cost of actually querying a BigQuery. So that's a very nice feature and that's really for BigQuery, but that feature is there now for you to use from the SQL client. The other one is you can also, all these DDLs that I mentioned, there is one about Parquet tables. So you can actually spin up a Parquet file and then instantiate the table from there, which is also very nice. And you typically do that, right? You have a Parquet file and you want to spin it up and then access that data, or maybe join with your events. So you can do that after 2.15. And the other one is logic for better join selection. This is really, as I mentioned, the join node. Right now, all it's doing is a p-transform, and it's always doing a group by key. The expectation is here is that we are splitting the logic, so depending on the stats, so we are already introducing some of this smart way to recognize the cost of doing one way or the other, then we can actually decide based on the optimizer what option to use. So basically here is, that's still not there, but these are the building blocks to make that work. BigQuery, you query BigQuery, sorry about redundancy. And then if you get a small table, then actually you can use that data set as a side input. So rather than using always a co-group by key in your join node, you can actually sometimes decide, okay, now I'm going to do a side input, which is much quicker because I know that one of the sides is smaller. So you can actually decide that. At the moment, it's kind of hardcore. It's always going co-group by key. But that's the expectation from these features that we are implementing. And some resources for you to play with. So the official website and also the SQL shell, whatever I described it there. And same thing for Dataflow for the Sequel UI. And I think that's it. And now questions, right? Question and stickers. And then food. Yeah, I know I was between you and the food, so now you're free.
Hi, I'd be interested in learning from the previous speaker if he's now going to write all his Python 3 code in the parsubs in Beam SQL.
We have been looking at it, and yeah, and I think there's certainly lots of stuff that we can do using it. Yeah, for sure.
Yeah. So just as a follow-on to that, I just wonder, what the different use cases are. When would you use Beam SQL as opposed to hand cranking your Pardoos?
It really depends on the type of use case. If you can represent your logic with a SQL, it's typically much better, right? Like if you will do, now for example, if you can represent, let's take example of a Spark. So if you can represent with a Spark SQL, you go easy and you go that way. But if you need to go one level low detail in terms of how it is, and I need to get that element and doing something with a UDF function, sometimes it's better to actually forget about SQL and then doing the kind of low level detail.
I don't think we can replace everything we do with it, but
yeah.
for sure I think there's a lot that we can.
That's right, because your join, that needs quite a lot of logic, right?
Yeah.
It's not like a simple join based on an equality condition, I will guess. Yeah,
exactly.
Yeah, but it's a good question, yeah. This is only, the SQL transform is only available in Java SDK at the moment. That's, yeah, but we're working on making that available in Python, yeah, step by step. Well, not us, but the whole community, right? We're talking, this is not really a Google Dataflow thing. This is all the Beam framework itself to actually being able to leverage SQL, because CalSite and all these components are actually open source. So it has nothing to do with the Dataflow runner, really. Yeah. Thank you.
Hi. I really like Beam SQL. It's like, it was frustrating not be able to use it in Python, and I knew that it's not supported. You did an example about like streaming from PubSub. Of course, is the main use case. Can you do it instead with other other resources as a batch, like from a BigQuery table?
Yes, you can do it in batch mode as well. Yeah. So you can definitely. The only thing is this is advanced. It's a different use case because you need to take into account that it's an unbound data set, right? So if you don't put a limit, as I did, it will constantly be running. So if you are expecting to get rows, you won't get them. If you are streaming into a table, that's fine because you stream as you stream, that's fine. You are actually inserting as they go. But limit is really to finish and then show you the results, which is kind of more about when you're experimenting. But yeah, you can.
No, because we encounter sometimes like the resource exceeded error in BigQuery when query like hundreds of tables at the same time. And I was wondering if this could actually help because you spin up your cluster and then maybe resource is higher.
Yeah, that's always a bit of a trade-off, right? Because the nice thing about BigQuery is you push down into the Dremel workers and they do the heavy work. Obviously, there are limitations in terms of shuffling. Same concept, hotkeys is a typical killer with BigQuery. When everything goes into a particular Dremel node, it blows up the memory because it has limits. So you need to actually play smart with how you run your query, with the keys and all that stuff. If you can go that way, it's always better because otherwise you need to pull out all the data from BigQuery, do the crunching, and put it back. It depends, really, it's a trade-off. But yeah, you always have that option.
Thank you.
Cheers.
Hey, thank you very much for the talk. It was really good. I'm a little curious, so forgive me for bombarding you with the questions. So the first question is is it possible to see the query plan before running the actual query? And sorry, go on.
No, it's a good question. You can enable debug mode, and then you see more information. What you see is the execution plan because you see the DAC. If you're submitting that into a Dataflow runner, obviously you submit that into a Flink runner, you will see that execution plan, but the actual execution plan with the nodes. But it's not that much different. The logical one is just really a mapping one-to-one, as I showed before. So if you have a bunch of filtering, joins, and so on, you will see that directly mapping one-to-one into the execution plan that you see in the DAC, in Dataflow UI or in Flink or Spark or whatever. In the direct runner, I don't think you can see that because it's more everything happening in memory, and yeah, it's nothing distributed really, nothing optimized that much. Yeah.
Sure. And Java SDK provides quite good primitives for testing.
Yeah.
Now, this may sound like a classic SQL testing example, but do you have any tips around that?
Well, that's a good question. If you look at the repo, the Beam repo, these functions, these methods, all these modules, they have test cases there. So you can actually see how they're doing it. Majority of these cases, there is a section about testing the client itself, which is a part, but the other one is purely using the SQL transform. So sure. I think majority of the stuff you can, as I mentioned, there are two paths, right? So there is the path about the JDBC client, that's one, which you probably, all you want to test is really the client on isolation, and then the logic and the parsing and all the stuff, because it's equivalent, that big box on the right, when I shared the slide. You can run that from SQL transforms, like any other pipeline, so you can do that in a very similar way to any other test within Beam SDK.
Sure. Yeah. One last question. Does it actually support nested queries? And do you have any plans of supporting the big table as a source?
Good questions. Nested, they are supported. The struct maps, I think they are not supported because there is no direct mapping within calcite, I think. Something I didn't mention is we're using calcite for all the when you define your DDLs, when you run your SQLs, they are defined in a particular way, right? SQL standard. We also have Zeta SQL. It's our own interpreter for SQL statements. Zeta SQL is open source, and it's actually the way we do the parsing within BigQuery. So you can actually switch. You can switch one or the other depending on what language you want to use. So you can use Zeta SQL if you are going to heavily use BigQuery. So it's compatible with all the latest features that you get out of BigQuery. But yeah, that's really the way that you will implement that. Yeah. What was the other question? Sorry.
Is there any immediate plans of supporting Bigtable?
Yeah, Bigtable I think there's a Jira that they're working on if it's not there already. I think there are some features that are not there, but you can always, as I mentioned, you can always have your source, transform that into a P collection of rows, and you can query that. So you can always map against any source that you have, but you need to do that step of mapping into a row. Yeah.
Great, thank you.
No problem, thank you.
Cool, more questions?
Oh, yeah.
No, good talk, David. I would like now if it's available the Cloud Dataflow engine in the REST API of BigQuery. Can we access? I don't know if it's available.
Yes, it's available. So you need to enable the APIs, and again, it's alpha, so this is not for production. Anyway, that's really for experimentation, prototyping kind of thing, right? So you will, anyway, there is no way you can make that part of your production pipeline anyway. But yeah, it's alpha and it's public alpha. You don't need to request access to the.
Great.
The only thing is that there's a big note there because it's alpha. We do maintenance because we always kind of add new features until we stabilize and we go into beta. So there is a maintenance window of every Monday or something that goes down. Yeah.
Yeah. Thank you.
No problem.
So if you're running this against BigQuery, does that row structure mean you have to have a flat table, or can you put nested elements within?
Yes, you can. It's a struct, so you can actually map that. It's a struct that maps directly into a row, yeah. So you have the only one is not available is maps when you want to use maps, but arrays. arrays, a struct for sure, because what I use with the JSON payload, that's actually a struct, and that goes, it's split anyway, but that's compatible with BigQuery. The only ones I'm not 100% sure is arrays, but yeah, structs, which is the main nested structure, yes. Yeah.
More questions?
Any more?
My favorite part of the demo was that you ran it in Belgium.
I didn't fail. Believe me, I've been testing today and had a bit of hiccups. Thank you.
I think Isambard and David will actually stay around, so
yes.
We have some food now, if I'm not mistaken.
Yeah, it should be around, and we're gonna have pizzas and yeah, all happening.
Awesome.
Yeah, we also have Googlers there, have colleagues that they can also help you guys with machine learning, with yes. So yeah, enjoy.
Cool, stay around, enjoy. Thank you very much for coming.